Welcome to our latest edition of CSM Explained. My name is Timo Eich. I am Business Development Manager at CSM. And in the next 30 minutes, we will be dealing with a really powerful topic in the truest sense of the word. Namely, we will talk about autonomous power measurement. Electrical power measurements and power analysis are probably one of the most important, if not the most important group of measurements in hybrid and electric vehicles when it comes to developing, optimizing, and testing the drive system. After all, compared to combustion engine technology, the electric components of the powertrain are still relatively young, and there's not that much experience on them. In addition, the current political establishment is demanding and forcing the widespread introduction of these new e-drive systems, thus creating a great deal of pressure on the manufacturers, but also on the end customers. And at the same time, it is primarily these end customers who partly are very critical when it comes to the performance and, above all, the range of new vehicle models. In addition, the breakthrough of electric mobility has finally reshuffled the cards in the international vehicle market, and there is now extremely strong competition in all areas and segments. At first, this means that power measurements and power analysis often have to be carried out under great time pressure. And at the same time, the quality of the measurements must meet high standards because consumers, perhaps more than ever, are looking particularly closely at what they spend their money on. Autonomous power measurements and analysis therefore help our test departments of vehicle manufacturers, suppliers, and engineering service providers to save time during road tests and also on test benches, and simply take the pressure off our test personnel if they are carried out well and with the right equipment. And how that can work, that's what we are looking together today. So today we are going to talk about autonomous power measurement, and maybe you've already noticed in my introduction that I've also talked about power analysis as well. Now ask yourself the following question. Are there any differences at all between power measurements and power analysis? And if so, what do these differences look like? And I'll say it right away, yes, there are differences between the two. And first of all, let's note that this collective term, power measurement, power analysis, covers a multitude of different measurement applications. And these respective applications have partly very different technical requirements. These different requirements result in a very different demand for measurement equipment. For example, in terms of measurement accuracy, range of application, connectivity, and also available functions. And with that, we also find very different budget requirements because simple applications can usually be solved much more cheaply than more complex applications. And this brings us, in addition to the time savings mentioned at the beginning, to the second point that companies are concerned about, and that are costs. Time efficiency and cost efficiency. This is what, in our experience, drives nearly every user in the testing sector. Well, first of all, let's take a look at the right side here in the picture, the power analysis section. And power analysis is primarily about developing and improving components and systems. So these are the applications where our developers want to take a very close look to get the latest bit of potential out of the components and make complete systems even more stable and powerful. Generally speaking, these are applications in which we have to acquire current and voltage values from two or more measuring points in the system in a highly synchronous manner, and then calculate them, usually across distributed measurement modules. Well, to do this, we need an extremely good synchronization mechanism and a computing unit on the meter level, which gets data from all the measurement modules simultaneously. We need a computing unit that can process very highly dynamic measurement signals from different synchronized signal sources in real time. An application for this is the determination of the inverter efficiency. Another characteristic of power analysis is that complex mathematical analyses are usually performed with the raw signals. For example, when analyzing electric motors, a star-delta transformation is usually calculated from the raw signals of voltage and current in order to determine the winding voltages and currents. And this requires an extremely powerful computing instance on a meter level. Power analysis usually also include applications in which highly dynamic processes are investigated, such as motor run-ups, which require dynamic and automatic period detection of voltage and current signals, or in which short integration intervals are required. For this, again, we need, in addition to high-speed measurement technology, a very powerful computing unit on a meter level. Well, let's take a look at the power measurement on the left side. How is the power measurement characterized? Well, the pure power measurement is initially nothing more than a watt meter, meaning a power meter. And with such a power meter, we can easily determine an actual state, a status quo. For example, a power meter is a great way to determine the power output of energy sources such as high voltage batteries or fuel cell systems. And with our power meter, we can also determine the power consumption of electrical consumers and components very well, of which we find quite a lot, especially in electric and hybrid vehicles. And in contrast to the power analysis, the calculation of relatively easy to determine main power values such as active power, reactive power, apparent power, and the active power factor are completely sufficient for us here. Of course, we also need those values for our power analysis, which is why we could also say that power measurement is simply an important process step within a power analysis procedure. Nevertheless, power measurements stand for themselves in many applications and are completely sufficient in various cases. And here we have compared these many different cases for you. This table has no claim to completeness and should serve you on one hand as an orientation whether you need power measurement or already power analysis for your applications, and on the other hand, it shows that a really large number of DC and AC applications can be solved with power measurement and can therefore ultimately also be implemented with a smaller budget. Of course, I won't read the whole list to you now. You will have access to the slides in our CSM Explained archive after the event. Well, our webinar today is called Autonomous Power Measurement, which means that today we are dealing with the left side of the table and we are going to pick the consumption measurement according to WLTP as an example later. Let's now take a look at the requirements for mobile power measurements, which, for example, have been brought to us by many of our customers who oftentimes had the problem that their existing power meters and analyzers were, on the one hand, too much capable, and on the other hand, too less robust for road testing. And many users are looking just for that. They are looking for power meters for mobile use. This means little space, harsh environment conditions, highly EMC loaded environment. What does this mean for the measuring devices? The devices must be as compact as possible. The device housings must be very robust. The housings must be really easy to install. And the housings must provide protection class IP65 or higher. What's more, a power meter should not only calculate the instantaneous power, meaning simply multiply voltage and current values, but it should also calculate important power parameters such as the active power, the apparent power, the reactive power, and the active power factor. And thus, mathematical functions with measurement value windows are necessary. Also, due to the highly EMC loaded environments in electric vehicles, it is important to calculate the RMS values of voltage and current. This is the only way that the power meter can evaluate the measured values correctly, even in the event of AC overlays, as they are, for example, imprinted by inverter clocking on the HV battery or current or voltage dips. And finally, only few people want to have a pointer instrument and write down the values by hand. Instead, our power meter should be able to forward the measurement data simply, quickly, and reliably to the data acquisition system, for example, to a data logger in the road test or a standard test bench system. And for this, our power measuring device should requires suitable bus interfaces and protocols. So our developers at CSM have taken all these requirements to their hearts and implemented them into the HV breakout measurement module family for power measurement. And based on the various components in and around the vehicle, I will show you below how we at CSM prefer to measure the power fluxes between these very components. So we see here on the left an AC charging station, a wall box, for example, of course, outside of the vehicle. Then follows, now already inside the vehicle, the onboard charger, the so-called OBC, which receives 1 to 3 phase AC power from the charging station, or in the future, perhaps vice versa, feeds it into the charging station. Keyword vehicle to grid. The OBC is then connected to the HV battery, meaning the AC voltage must be rectified in the OBC in order to feed it into the HV battery, and the HV battery then supplies, for example, the traction inverter with DC voltage, which is then in turn converted into a three-phase AC voltage for the electric motor. Now let's start with the power measurement between HV battery and inverter. And to do so, we insert an HVBM 1.2, an one phase measuring power meter for 2 single core high voltage lines, plus and minus separated, directly into the lines. So why do we do this way? Because our HVBM 1.2 now measures the HV voltage and current directly and without any analog transmission path exactly where they occur. Therefore, the HVBM has to be robust, and as you can see, the HVBM offers IP67 protection and an operating temperature range of -40 up to 125 degrees centigrade. So you could get started in winter testing as well as in the desert. Now, what's very important, the current measurement is conducted with a fully temperature compensated shunt module, and it is possible to measure inner conductor currents up to plus minus 2000 amps. Voltages can be measured up to plus minus 2000 volts, and the data acquisition is performed with a sampling rate of 1 million measuring points per second and per channel. That's 1 megahertz sampling rate. And for the data transmission, the HVBM offers 2 interfaces that operate independently. For the fast raw data, the device has an EtherCAT interface, a very common option for data transmission in test benches. And for recording, for example, in long-term field trials with reduced data rate, an additional CAN interface is available. The high voltage cables can now be connected in different ways. For example, end of line test benches where a quick change of the test items is important with the power lock connection system, high voltage plug-in system, or for our road tests, usually via cable glance. And with us, you even have the option of having your customized plug-and-play adapters manufactured. And this is then really plug and play. You take the original cable out of your vehicle and plug in the instrumented cable with the HVBM instead, including a connected interlock. And since the HVBM has all the sensors on board, so to speak, is also delivered completely calibrated and is ready for immediate use. So you will really save time when instrumenting. So our HVBM 1.2 has been inserted into the lines between the battery and the inverter and can now get started, meaning to measure current and voltage fully synchronously, and of course now also calculate the power. That is what we are primarily concerned with today. And now the question is, how does the HVBM now calculate the power? And for this purpose, the HVBM takes the measured signals of current and voltage and calculates on board and in real time the active, the reactive, the apparent power, as well as the power factor. In addition, the HVBM calculates the RMS values of voltage and current. For all of those calculations, no additional computing instance is needed. The HVBM calculates all those important values completely autonomously. And we have then already fulfilled two of the requirements of our customers. If you remember the required power characteristic values here on the upper box and the RMS values. The measuring circuit in the HVBM for one-phase power measurement is really not witchcraft. We measure the current with the fully temperature compensated shunt module in the minus path and the voltage between the two conductors HV plus and HV minus. And what probably interests you even more is now how the whole thing then looks like in the configuration software. Well, here is now the device settings for the HVBMs 1.2 in our CSM config software. In the setting channels, you can select whether you want to use only the voltage, voltage and current, voltage, current and instantaneous power, so only U times I, or whether you want to activate the additional power channels. And if you activate the HVBM's calculated functions, then you now get 6 additional virtual channels here on our one-phase meter, namely the RMS values of U and I, as well as the active, the apparent, the reactive power, and the active power factor lambda. And you can then transmit these virtual channels via the CAN bus for data acquisition. Now it is important that you set the integration time for the power channels, and you can now freely select between 10 milliseconds and 10 seconds, and you simply enter the value in the corresponding field here, and this integration time is then fixed for the duration of the measurement. For signals with strong frequency changes, you should then enter longer integration intervals, because otherwise the power calculations can become inaccurate. And our HVBM 1.2 now transmits the calculated power parameters via the CAN bus, here represented by the blue line in our visualization. And that means that the HVBM measures, calculates onboard, and finally transmits important power values, and that completely standalone. Now we proceed to the three-phase power measurement between the inverter and the e-motor, and here we also insert a HV breakout module directly into the three phases. Here now an HVBM 3.3 for the three-phase AC power measurements. So the HVBM 3.3 now measures 3 voltages and 3 currents with the same technology as the HVBM 1.2, and the HVBM 3.3 can even measure twice as fast. Here we now achieve sampling rates at 2 million data points per second, meaning 2 megahertz per measurement channel. And these fast raw signals are then transmitted to the data acquisition via XCP on Ethernet, also a widely used standard. Of course, our HBM 3.3 also calculates the power values on board and in real time itself. And now let's take a look at the measurement circuit of the HBM 3.3. The HBM 3.3 determines the power values using the 2-watt meter method. In the so-called Aaron circuit, the power is determined once from U12 and I1 and the power from U23 and I2, and these two values are then added together. This is a relatively common method that is sufficient for many applications. This is then how the whole thing looks like in the configuration software. Above, we see the 6 raw signals from 3 times voltage and 3 times current. And in addition, there are now the 6 associated RMS values, as well as the active, the apparent, the reactive power, and the active power factor. And these values are now all available as virtual channels for transmission and further processing. Also here, the integration time is fixed between 10 milliseconds and 10 seconds. And here with the AC measurement, you as a professional will already recognize that this calculation principle also comes to its limits with very specific, more demanding applications, for example, with dynamic load changes. Because then you simply need the dynamic detection of the period duration from the raw signals as it is implemented in the vector e-mobility analyzer, for example. The principle of the Aaron circuit then also partially reached its limit due to the assumptions from the 2-watt meter method. So no leakage current and no unbalances on the 3 phases are taken into account. Here again, the vector CSM e-mobility analyzer helps because it calculates all partial power values from all 3 voltage and current signals of the HBM 3.3 and is thus also well equipped for complex applications such as e-motor analysis, for example. But if you don't have such requirements at all, you can achieve excellent results with the calculation functions of the HBM 3.3. And the nice thing is, if you then do have more demanding applications in the future, you measure with the same hardware and then simply outsource the power calculations to Vector's e-mobility analyzer. This also means that with the HVBM modules, you have quite a cheap entry into power measurement and can then upgrade at any time as your requirements increase by performing the power calculations with Vector's e-mobility analyzer, which is an integral part of the Canopy and vMeasure software suites. Also here again visualize how the calculated power values as well as the raw signals can be transmitted once here now by XCP on Ethernet. This is the black line here, and also again by the CAN bus here in blue. And just to emphasize that again, the HVBM measures, calculates on board and transmits ready to use power values completely standalone. That is what we mean by autonomous power measurement. And now we also add data acquisition tools to our picture because the receivers from our power values as well as the raw signals can now be data loggers. Here in the picture, our UniCAN 3 logger with CAN connection. It could be a measuring PC in the vehicle which has an XCP interface, or it could also be the computer of an automation system of your test bench, which receives the data, for example, via EtherCAT. The advantage is that using the onboard power channels calculated on the HVBM results in a massively reduced data stream, which of course does not load the measuring computer nearly as much as fast raw signals. This means that the CPU of the measuring computer is spared. And of course, the automation system can now continue to work directly with the characteristic power values, another huge advantage. This also means that no further software tools are required for the power measurement on the data acquisition side, and this again saves costs. The power values generated by the HCBM can be used directly in various software suites, for example, in ETA's Inca, in AVL Puma, in KS Engineer's Tornado, in Kratzer's PA Tool, and many more. Although the HVBM modules have been designed for road tests, they are equally efficient on test benches. And if you then use the same measurement technology both for the road test and on the test benches, the measured values from both scenarios are even directly comparable, one-to-one, due to the same technical properties such as filter and group runtimes. The HV breakout modules with their power calculation channels thus meet the most essential requirements from practice. Here again, the slide from the beginning as a reminder, designed for road test and test bench, calculation of the main power characteristics, RMS calculation for superpositions and disturbances, and multiple data transmission options. Well, I promised to you an example, and here it comes, namely the WLTP measurement. In the WLTP measurement, the standardized WLTP cycle is driven with a fully charged vehicle, and then when the vehicle is charged up again, you measure how much energy was consumed while driving the WLTP cycle. And to do this, you measure the power between the charging station here and the vehicle's OBC, for example. For this purpose, we use an HVBM 3.1 OBC here between the charging station and the OBC, which has been specially developed by CSM for measurements concerning AC charging. In contrast to the AC power measurement between the inverter and the electric motor, three-phase AC measurements between the charging station and the OBC usually involves a neutral conductor in addition to the three phases. This means that in the measuring circuit of the HVBM 3.1 OBC, all three voltages of the three phases are measured against neutral or PE, and that's then a star circuit. The currents are, of course, measured again by means of fully compensated shunt modules directly in the three respective phases. And in this way, the HVBM 3.1 OBC can relatively easily calculate the power characteristics directly from the raw data without having to use this little trick like the 2-watt meter method. And here we now also see real measurement data from the beginning of a one-phase AC charging process here from a Renault Zoe. In the upper curve here, in the upper curve window, we now see the RMS values of voltage and current. So the voltage is here the light blue curve, and the current we see here in red. And in the lower curve window, you can now see in green here the active power, which has now directly been calculated on board in the HVBM. In addition, we now see this ramp here in pink, which is the integral of the active power, meaning the summed up usable energy that is transferred between the charging station and the OBC during charging. But what is also noticeable here is that between seconds 12 and 15, there is a phase where the current is already flowing, a current of approximately 3 amperes here, but no active power can be measured. We can only see active power from second 15. Well, since we have also calculated the apparent and the reactive power with the HVBM 3.1 OBC, we can now see here that in these 3 seconds, there is exclusively a reactive power component, meaning energy that our OPC cannot utilize at all. The reactive power is shown here in purple, and in the first 3 seconds, it is more or less congruent with the apparent power, the curve in orange here. And only after these 3 seconds, when the charging current increases again strongly, only then does our active power component kick in. Here again in green, and it's increasing strongly, and with it logically also the apparent power, the orange curve. And you can also observe this phenomenon wonderfully here on the yellow curve in the middle, because the active power factor, the yellow curve here in the middle, is also close to 0 within those 3 seconds, and then only rises to a good 90 to 95% when the active power also rises. By the way, we will discuss what these charging processes are all about in another episode of CSM Explained in a few weeks. This measurement was an example of how professional power measurements can be performed with HV breakout modules and their power calculation channels. And here, the list again on the right shows in conclusion that many more applications that can basically be implemented just as reliably with the HVBM and their calculation functions. Of course, you should always check the criteria mentioned at the beginning in each individual case. And if you are unsure and need help, our experts will of course be happy to assist you. This brings me to the end of my presentation. I hope that I could show you that we at CSM mean what we at CSM mean by autonomous power measurement, and how this can be implemented in practice, for example, with our HV breakout modules.